recalling something we saw last time, right? So we have the inverse function theorem where, so let me just draw a picture. So you have this open set U in Rn. You have a smooth map, mapping it to somewhere f of u. This is sitting inside Rn also. And suppose at a point, you know that the derivative of f, which is an n by n matrix in this case, so that's the total derivative. So f from u to Rn is smooth, and df at a point x is invertible. So this derivative is an isomorphism. And here it's from Rn to Rn. So what we want is that, so there's a linear map. So remember that this derivative, the linear map from Rn to Rn. So thus being invertible, just in this case, is linear maps from Rn to itself. It just means it's an isomorphism, right? So you have this setup, and so then the conclusion is that it's actually f is actually a local diffeomorphism, right? F is a local diffeo around x, and what it means is that there is some neighborhood, let's call it V, around x, and some neighborhood on W, so that f restricted to V is a diffeomorphism to W. Right? W is some neighborhood, so there exists V and W. I'm not writing everything. We saw a statement last time. So this is what it means, right? So in other words, so in this neighborhood W of f of x, one can define an inverse, right? So there's an f inverse that you can define on that. It's a local inverse. Right? That's the inverse function, okay, of the inverse function theorem. Okay, so this is what the inverse function theorem is, and let me tell you a little bit. I assume that people have seen the proof, but let me just remind you. So it uses, one of the proofs uses the contraction mapping principle, and what does this say? Well, in this context, we're just going to need it on, let's say, closed balls to itself. So suppose you have a map. Let's call it F again, from a closed ball. We call it. All these in Euclidean spaces, right? So this is an Rn. Rn. Let me call that B, ball B instead. So B. B to B, where B is a closed ball in Rn, and such that it's contracting. So the distance between the images here, if I think of it as an Rn, I can use the usual Euclidean distance. So if you take images of 2 points x and x prime, it's going to be less than some constant times the distance between x and x prime. So distance between f of x and f of x prime is less than c time, where c is something strictly less than 1. Okay, so it's the distances are decreasing. So if you look at the images, so then the contraction mapping principle or contraction mapping theorem says then f has a fixed point. In fact, it's a unique fixed point in B, right? So in other words, there's some point x naught in B where f of x naught is equal to x naught, right? That's a fixed point. Okay, so how does this get used? So I'm going to talk about how this F inverse is sort of constructed. So the point, one of the things that's not given to us, right? F is just, all that we know is that the derivative at x is invertible, right? This is all that's given to us. So even showing that there exists some neighborhood where F is injective is not automatic, and so unless it's injective, we can't even define F inverse on some neighborhood here, right? So I'm going to sort of talk about that step, and that's the step that uses the contraction mapping principle. So how does that go? So how do you construct the inverse once you know that just the derivative is invertible? Well, so let's first, here's the idea of the proof. So I'm going to also do some other assumptions. We can assume, without loss of generality, that the point X that we chose is at the origin. Okay, so this point, so this is just by translating things around, right? I can make sure that this point X is really the origin, and I can also assume that the derivative that we said was invertible, so that's the derivative at the point X, which is now origin. So that's just the identity transformation, so the identity map from Rn to Rn. So how can we assume that? Well, we can just do that by post-composing F. If you change F by a linear map, a dF of 0 inverse. So let me just kind of try to indicate here. So if we, so we can just sort of post-compose this by some map of Rn to Rn, which is a linear map which is just given by dF, this derivative inverse. And then if you look at the composition now of that with this linear map, so then this composition would, by the chain rule, have derivative identity at point X. Okay, and it's easy to see that if you can prove this inverse function theorem for that composition, then you can also prove it for this guy, because that linear map I was talking about is an isomorphism, right? It's a linear map defined in whole of Rn, so it's, in other words, it's also invertible. Okay, so in any case, so you can convince yourself, perhaps this is some assumption that you can do, and so you can make this assumption, and you can now sort of the rest of the proof is as follows. You define the function g of x, x minus f of x. Okay, and then so notice that the derivative of g at the point 0, wait, I was calling it capital F. Well, let me call this small. So I was using small letters, not capital. So let me call these little g. Okay. So now that the derivative at 0 is 0 now, because so the derivative of f at 0 is identity, and so is the derivative of this map. This is just the identity. This part is just the identity map. Okay, so and g is clearly also a smooth function in a neighborhood of that point. I mean, it's a smooth function defined on actually on the whole of its original domain U. But in particular, it'll mean that the size of the derivative, the norm of the derivative, which you can define this norm in various ways. Let me not go too much into that. You can think of this as you sum up all the entries of, you square all the entries of those matrix and sum it up and take a square root, perhaps. That might be a definition of a norm. So this is less than half in a closed ball around the origin. Let me call the ball radius 2r. Okay, and this is just by continuity, right? So this entries of this matrix would vary continuously. So if it is 0 somewhere, it's going to be this zeros, by the way, it's a zero matrix, right? This is actually an n by n matrix with all entries zero. But if it's zero at this point, at this vector zero, so anywhere in the neighborhood of zero, it will continue being very small. And in particular, these entries would be less than half, or the L2 norm, or whatever norm you choose is going to be small. And in particular, you can make it small. I mean, this half I've chosen here to be, maybe it should be 1/4.
So,
yes.
So you mean norm of dgx, right, is less than half for all x in a closure?
Yeah, sorry. Yeah, that's right. Thank you. Yes. Okay. So in a closed ball, it means that for all x in this. Yes, thanks. Okay. So let me just push this down. Yeah, and this implies by the mean value theorem that the norm of G is less than x by 2. Okay, so for all x in this closed, in a smaller closed ball. Okay, yeah, so here I'm kind of, yeah, so I guess, so here's, I'm just using the fact that, what does mean value theorem say? It just says that, so g of x minus g of 0 would be less than df of some, some point c times the norm of x, right? And so, so this is, by our assumption, is less than half. So maybe this is actually strictly less than half. But anyway, I don't care right now about whether it's strictly. So let me just, maybe I'll put strictly here. Okay, and this in turn tells you that if you look at the map, so then let me come back to blue. So then for any y in this closed ball of size r by 2, if you look at the function, the new map, g of x plus y. Okay, if you look at this new map, then this maps, so this closed ball radius r to itself. Okay, so you can sort of convince yourself of that, because so what happens is, oops, I need to push this down. So I keep running out of space here. Okay, yeah, right. This is to come. So yeah, so yeah, by assumption, if you're inside x, so if you're inside this ball of radius r, let's see if we got this right. So if you're inside this ball of radius r, then you know that your g of x will be inside a ball of radius r by 2, because you are, sort of, if you have this factor half here, and then y is also inside a ball of radius r by 2. So at most you'll be kind of going a distance r if you do this addition. So this guy, this g of y for any fixed y in that ball of radius r by 2 actually defines this map from a closed ball to itself. And moreover, it's a contracting map. Okay, so and is a contraction. Why? Because G is a contraction. That's what this. Okay, again, I sort of mixed up my small g's and capital G's. So let me just change these to small g's. So this little g, this map is a contraction, right? Because it's less than half times, right? so this is well, you can so this sort of, yeah, so there's a contraction on this domain, right? So but this is just, if you fix a y, this is just a translation. So this is still contractions. If you look at the something like definition of a contraction, these y's would cancel out when you subtract g of x. So gy of x and gy of x prime, let's say. Okay, so this is a contraction, and so the contraction mapping principle now tells you that the contraction mapping theorem tells you that this gy has a fixed point. Okay, so there exists some, let's call it x naught for some x naught in B of 0R closure. Okay, and what does that mean? It means if you look at the definition of g of y, it's g of x naught plus y equals x naught. Or if you look at how g was defined, it just means x naught minus f of x naught plus y equals x naught, which just means that f of x naught equals y. Okay, so what you've been able to do is you've found, so there exists some x naught that maps to y. That's what you've done. Okay, so so hence you can define f inverse on B of 0R by 2. Let's call it that. Okay, so that's where y was. Okay, so y was inside this. So by the way, this also, I mean, there's also uniqueness in but anyway, that doesn't matter. But this actually tells you that there is this, you can construct an inverse here. Yeah, so there's actually, so maybe it does matter here. So I'll just say that for some unique choice of x naught, right? That the contraction mapping theorem tells you there's a unique point x naught, which is a fixed point. So that's the fixed point x, and so the map y going to x naught is our inverse map for f. Okay, so that's how you know that there is a, so in a neighborhood, you can define the inverse. So at least in this neighborhood, in this green neighborhood W, there is a map going back, so that, you know, so that this compositions of the identity. I mean, in other words, this f is going to be injective here. So every point y in this some small neighborhood, you will get an x naught which maps there. Okay, so this is actually the most important step, and then you can so the next step, which I won't do, is to sort of actually prove that this map f inverse that we construct this way is smooth, and that sort of depends the fact that f we know is smooth, and so sort of it's only, yeah, you have to basically show that this fixed point that you get this varies smoothly as you sort of change your y smoothly. If you vary your y smoothly, then your fixed point also varies smoothly. That's the sort of the rest of the argument. Okay, but anyway, so that's the proof of the inverse function theorem. And one of the consequences that I wanted to mention is that you can construct manifolds using the inverse function theorem. So suppose you start with a smooth map from U to Rp, where P is less than n. So your domain is something in a larger Euclidean space, of some Euclidean space of larger dimension, and your target is lesser dimension. You have a smooth map with the property that this happens. So this derivative, so now what's the derivative? The derivative is going to be some at any point x in U, is going to be a linear map from Rn to Rp, right? And so this is a vector space of dimension n in the domain and dimension p, which is smaller in the target. And so you can talk of the you can't talk of those map being invertible anymore. You know, if it's invertible, it needs to the two vector spaces need to have the same dimension. But you can talk of this linear map having full rank. Okay, so being surjective. And that's this notion. So that's what you call, you know, this derivative having rank p. That just means that this linear map has rank p, and you have that property whenever g of x is equal to 0. Right? So so I'll give you an example in a minute. But so suppose this happens. Suppose you have all this. You have the smooth map, so that it has this property that the derivative is full rank whenever you're looking, whenever g of x is equal to 0. So you're looking at a pre-image of 0. Okay, so all the points that maps to 0 in Rp. And for all those points, you have this property of derivative being full rank. So then the conclusion is that this pre-image that we're talking about, so we just mentioned here, this pre-image is actually a manifold. So is a n minus p dimensional manifold. Okay, so and so before, maybe I'll just mention an example very quickly before we talk about the proof. So this is the one example is so suppose your G is a suppose your P is just 1, so that your G is actually a function, and you define the function this way. It's the sum of squares of these coordinates.
Excuse me, sir.
Yes.
This G minus G inverse of 0, is it something similar to regular surfaces? Like where that
Yeah, absolutely. Yeah, this exactly. This will be the notion of a regular pre-image later on. Yeah, I haven't yet defined what a regular value all that means, but yes, so these are going to be yeah. So this is, you might have come across some of these things before. So this is an example. So suppose you have start with a function, a g, and you look at these this function. It's easy to check that this satisfies our condition. Okay, so here the derivative needs to only have rank 1, right? And what's the derivative? Well, it's going to be, well, the derivative at any point, well, in this case, it will just be this, well, I guess in the way I set it up, it's a column vector. But in any case, it's either going to be a column vector or a row vector, sort of something like this. And this thing vanishes only when x1, x2 up to xn is all 0. But that doesn't happen in the pre-image of 0 in this case. Okay, so because if all of these x1, x2 are all 0, then your value is -1 and you're not 0. Okay, so this satisfies our condition, and so by the previous theorems, the G inverse of 0 is a manifold. What manifold is it? Can somebody tell me?
It's a sphere of radius 1.
Yeah, which sphere is it?
Radius 1. Unit sphere.
It's Sn minus 1.
Yeah, that's right. So it's a manifold Sn minus 1, right? So it's a sort of the diffeomorphic to Sn minus 1. Yeah, that's right. Yeah, so it's right. I mean, it's the unit sphere sitting inside Rn, but the way we've defined Sn minus 1 is intrinsic. It's nothing to do with it sitting inside anywhere, right? So it's we defined it using charts. So you kind of piece together some charts and you get something. But you're right. I mean, this is sort of the, yeah. I guess we also kind of had in mind the unit sphere when we talked about giving charts to things. So yes, that's right. So, but it is this n-1 dimensional sphere. All right, but so this is an example, but how's this proved? So here's the proof. Well, suppose, so you start with this, right? So so we can assume actually, so that so we are looking at this derivative, right? So we're looking at the derivative of g, and we know that has rank p, right? But it's so we can make sure that it's the first p variables that may so that it's an invertible. Yeah. So the first p variables is what contributes to the rank. So that this is a p by p matrix, it's the sub matrix of the total derivative, and this matrix has rank p. So we can arrange that. I mean, so we can arrange that by maybe sort of permuting variables, right? So we want to make sure that all the variables that do contribute to the rank are sort of are the first p variables here, and so by and that rearrangement is something like post composing, or let's see, I mean, it's either pre-composing with some, maybe it's pre-composing by some homeomorphism of Rn to Rn that sort of permutes the variables, and that's a homeomorphism of Rn to Rn. So it's actually a diffeomorphism of Rn to Rn. So that won't change anything, right? So we can assume that it's the first p variables that actually sort of makes it rank p, makes it a rank p matrix, and so then this square matrix would be invertible. Okay, so that's the initial assumption, and then you want to apply the inverse function theorem, except that sort of this target has lesser dimension, right? So inverse function theorem, you can talk of the derivative being invertible only the domain and range have the same dimension. So you kind of correct for that. You define this map capital G from Rn to Rp cross R of n minus p. Okay, so now the domain and the range have the same dimension. Okay, and the way that you define this map is you send x1 to xn to g of x1 to xn. So that lives in this factor Rp, and then the rest is just a identity map. Okay, so somehow this from the coordinate xp onwards, so this xp plus 1 onwards, so that part just maps by the identity. Okay, so you've kind of extended the dimension, you've increased the dimension of your target, if you like. And so now if you compute the derivative of this total map, well, the first p variables is exactly this map. Well, maybe I should mention this is the sort of that sub matrix which is invertible. This is sort of the ij less than equal to p, because this was this matrix that we had before. Okay, so involving the first p variables. Okay, so this appears here. This part is 0, and there's the identity map here. Okay, and there's something here which we don't care about right now, right? So this is what this total derivative for this map G would look like, and then you see that this is also invertible at any point where g of x is equal to 0, because then this would be invertible, and that would make this whole thing invertible, right? So the determinant of this matrix is determinant of this submatrix times the determinant of the identity map, which is just 1, right? So everything depends on this part being invertible, and that is guaranteed by assumption whenever g of x is equal to 0. Remember, on the pre-image of 0, you have this property of this part being invertible. Okay, so now at least we have a map where we can apply the inverse function theorem, right? Because this is going from Rn to Rn, and at such a point x, this total derivative is invertible. So by the inverse function theorem, there is a diffeomorphism which is like the inverse of this map capital G. So let me just maybe draw a picture here. But so kind of the thing to keep in mind is yeah, so maybe so this is the point. So this is the point. Let me call it, instead of x, I've called it A1 to AN. Okay, so this is in Rn, and I'm going to call this neighborhood V, and there's a map capital G here, and this is sending to W. It's going to be a diffeomorphism from V to W, and H is going to be the inverse. Okay, and so this A1 to AN lies in the pre-image. So suppose sort of the pre-image of 0 is somewhere here in the picture. So this is sort of the well, it's the set of points is G inverse of 0, right? So if something is in the pre-image of little g inverse of 0, so then it'll go to, so this part would be 0, right? So this is the first p coordinates would be 0, and the rest would be something. Well, we know what the something is because it's the same as things here. This point gets mapped to something like 0, 0, then a p plus 1, a p plus 2, a n, right? And so so W is a neighborhood of that point, and V is a neighborhood of that original point, and so the inverse function theorem guarantees that there's a map H that goes from W to V diffeomorphically. Okay, and what happens? If you look at V so this map would give you a chart also, because what happens is if you look at the map, if you look at this open set V intersected with G inverse of W, right? So so this map H will send, so here, so you can look at, you can fix the first 0, the first p variables to be 0. So, and then you can look at the rest as Rn minus p. Okay, so let me call it, let me do not, 0 cross this. Okay, now this is going to give you charts in a neighborhood of that point A1 to AN, because what's happening here is that so this part is well, it's basically you're varying these many coordinates, right? And you know that yeah, so this is your n minus p. So this whole thing actually, so let me just, so this whole thing is contained inside Rn minus p. You can think of it as, so you're restricting to some subspace of dimension n minus p, and your H will be a diffeomorphism from that to this. So this is a diffeomorphism. So let me just write. So this is a diffeomorphism. So this kind of, sort of, if you think, so H, originally H I've written is sort of, it's defined on this whole W, right? And it maps to V. But if you restrict yourself to this part of W, so W intersected with this slice, maybe I should draw the slice somewhere. So maybe I'll draw that in red. There's some slice here, Okay, this is this linear slice where sort of this plane of 0 cross Rn minus P. So if you restrict yourself to that slice, then H, the restriction of H will map to this pre-image G inverse of 0, because by definition, G, the capital G of any point. So by the definition, if you do H first and then G, you're the identity map, right? That's what a diffeomorphism is. So you know that if you start off with anything here, you have to end up in the pre-image of 0, because that's this part is G of 0, right? So the first P coordinates gives you G of G of whatever point, G of X, right? So if you're somewhere X here, this is G of X. Okay, so anyway, so you can sort of can sort of go back and sort of do some diagram chasing if you like to figure out that this is indeed, if you restrict H to this slice, you are getting a diffeomorphism to this open set that I've written on the left, and this is your parametrization, rather, not the chart. Chart is sort of maybe this way, but this is sort of in a neighborhood of this point A1 to AN. So this defines a neighborhood of that point, and so this is parameterized by some open set in Rn minus P. Okay, and that's what you want, out of a to have a manifold. You want that every point has a neighborhood. The other properties of or the things in the definition of a manifold are automatic. The fact that it is housed off and second countable, those you can easily prove, because after all, we are talking about the subsets of Euclidean space here, right? But this is the locally Euclidean part is obtained via the inverse function theorem this way. Okay. Actually, we'll see more of this a bit later. Perhaps it'll be more clearer. This is just maps from Rn to Rp, but later on we'll talk of a similar thing where you have maps from a manifold to another manifold of smaller dimensions. So we kind of, this is sort of a special case of something slightly more general where you can get can talk of these inverse images being sort of submanifolds. So let me actually define the notion of a submanifold here. So this is an example. This was this pre-image that we got was actually a submanifold of Rn. So let me just say that. So in what we saw, so that this pre-image is a submanifold of Rn. So what's a submanifold? So in general, if you can talk of submanifolds of any manifold, here I've taken X to be an n-dimensional manifold, and suppose you have a subset Y inside X. So that is a k-dimensional manifold where k is less than or equal to n. So if the following happens, well, if for any point in X, so let me just say, sorry, any point in Y. So if for any Y in capital Y, there exists a chart of phi from, so well, there exists a neighborhood. The first exists a neighborhood U of Y and a smooth map. Let me call it a smooth. Let me call it a diffeomorphism, not just a smooth map. It's a chart. Okay, it's a chart. It's a sort of a diffeo. So let's call it phi from U to Rn, but then Rn I want to think of it as Rk cross Rn minus k. Okay, and such that u intersected with y. That's the open set. So let me sort of draw the picture that we have. So this is my x, and maybe the y is some submanifold here. So I've taken a point y, little y here. That has a neighborhood u, and I want some map, the chart, to straighten out this submanifold. So the image of this portion, let's say, becomes, let's say, straight in some sense, and sort of this is so phi is going to map to, oops, maybe phi is going to map u to something in Rn, but the portion, the red portion, goes to a slice, and this is some slice is something living in, let's say this is sort of 0 cross R n minus k. Okay, so so this is exactly what was happening before. So let me finish writing this. So u intersection y equals phi inverse of okay, maybe the change things around. So this is maybe I should draw it this way. Maybe slightly different from what I just wrote earlier, but I'll think of it, this is RK cross 0. It's sort of some slice like this. So it's going to be pre-image of RK cross 0. Okay, so that it's parametrized by k, by some open set in RK, by k variables. Okay, so this is sort of what was going on here, except this k was n minus p. Okay, so here also it was a similar thing, where here the map phi is just this map G restricted to V, right? So that's a diffeomorphism. The inverse was H, right? And this G, what it does is straightens out. It sends this pre-image to this slice, right? And so and then sort of its restriction is a diffeomorphism, as I said. So if H, anyway, so yeah, so there's these k variables, let me call n minus pk. So there's k variables. When they vary, you move around in this slice, and this map H, they kind of parameterize this entire sort of neighborhood. This V intersection G inverse of 0 is parameterized by these k variables. So this is sort of the general kind of pictures, or locally it's the same. So, and that's called being a submanifold. That's what being a submanifold is. Okay, and of course, when I talk of in our context, everything is smooth, right? So when I talk of submanifold, these are all smooth maps, and so phi is smooth, etc. Okay, so we are always going to talk of things in the smooth category. Okay, so this is the notion of a submanifold, and I said so sort of maybe so let me just say we'll see. So there's a version of what we just saw for maps, smooth maps from some n-dimensional manifold to some p-dimensional manifold where n is bigger than p, and we need this property. So remember that if I go back to the statement of what we just saw, we had this kind of funny thing of this derivative having full rank for all these points of this. This is a special property. That this is called a submersion. Okay, so it's a so this is, we'll see. So let me say certain smooth maps. So which called submersions, and this we'll see maybe next time. Okay, so so one of the difficulties, we first need to kind of understand what it means for a derivative of a map between two manifolds. So this is something that already one of you had pointed out. I mean, so here for Euclidean spaces, the derivative, we know what it means. There's this linear map, right? But when you have a smooth map from some smooth manifold to another smooth manifold, right? You want a notion of a derivative that doesn't depend on the charts and things like that, right? You know, your charts was you had to choose some atlas, compatible atlas, but that shouldn't matter when you talk of, you know, sort of when you deal with manifolds, and that's one of the things that we'll have to do. So that's this notion of what a derivative of a map between two manifolds is. Okay, and so that's coming up next time. So that's called, you know, sort of tangent spaces and so on. Okay, so in this sort of abstract setting. So we're not talking of, remember, all these things, you know, these smooth manifolds, the way I've defined them, these are not subsets of some Rn necessarily. They are just, you know, some things, some topological spaces which locally look Euclidean, okay, and which carry this smooth atlas. Okay, and so so you can't quite think of it as something sitting inside some Euclidean space. But we'll later see that we can. That's the Whitney embedding theorem. But right now they are some sort of abstractly defined, intrinsically defined objects. Okay. All right. So before I go on to tangent spaces and all that, let me actually come back to one more thing that I guess I missed out, which is sort of the notion of Lie groups. So this also appears in the title of the course. So so we better see some examples. Although we mentioned that we mentioned some examples in passing, but let me just make a note of those. So Lie group, let's call it G. Here's the definition. Well, it's a smooth manifold, which is also a group. Okay, and it's not only a group, it's the group structure is compatible with being a smooth manifold. So it means that, you know, if you look at the multiplication map, that's the group operation. So let's say M of G H is G times H, right, in the group. So this is smooth, right? You want these multiplication maps to be smooth, and you also have the inversion map, right? Since it's a group, you can send any element to its inverse. So this is also smooth. Okay, so you want these two to also be smooth maps, and that's what means to be compatible with the smooth structure. Okay, so there's also the weaker notion of a topological group where you don't want these to be necessarily smooth, but you just want it to be continuous, right? These maps, multiplication map and the inversion map, to be continuous. And maybe you only think of it as a topological manifold, okay? But for us, we'll be interested in smooth, when everything is smooth, and that's a Lie group. Okay, and for example, what are examples? R and or Rn with the additive group structure is certainly a Lie group, right? Okay, so this is Rn with addition. If you look at another example is invertible n by n matrices with real entries, right? So invertible n by n matrices. That's why is that a Lie group? Well, you can think of that as open subset of something which is a manifold, which is all n by n matrices. So these are sort of n by n matrices with real entries. That's nothing but Rn squared, right? So you can just, instead of writing it as a square matrix, you can string together the entries to a single vector of size of length n squared. Okay, so this GL NR is a subset of this because being invertible just means that the determinant is non-zero, right? So and it's an open subset. So GLNR is pre-image. Well, it's a set of. Let me put it this way. So the determinant from which is defined in n cross R to R. So taking a matrix A to its determinant is continuous. It's clearly. It's by definition a determinant you know the expression of. It only involves products and sums of these variables. And then GL and R is just all those matrices so that the determinant is not zero. That's the sort of the definition, right? And so it's a pre-image of an open set in R, right? It's everything except zero. And so that's pre-image of an open set, a continuous map. That's an open set. So so GL and R is an open subset, and once you're an open subset of some in some manifold, you're automatically also a manifold because just it's just the inclusion map in some sense, right? So that's easy. So that gives you a nice example. Here's another example. SLNR, right? Let me write. Sometimes written like this. So that's the set of. It's a subset of GLNR, where you're looking at matrices with determinant 1. Okay, and why is this a manifold? Well, so this is a manifold. Because because of what we were discussing, actually, because you can prove that if you look at the determinant maps, so you're basically looking at the inverse image of 1, right? And you can prove that the points in this pre-image have full rank. In the pre-image have full rank. This is what it pre-image of 1. So this is also another way of saying that 1 is a regular value. Since somebody had mentioned the word regular, because 1 is a regular value of the determinant map. This is not hard to prove because what happens is if you look at a determinant, let's see. Yeah. So if you look at the determinant of a matrix Xij, something, let's say n by n matrix. All right, so you can, the way that it looks like, it looks like, let's take X11 entry. X11 entry times determinant of some smaller submatrix, this cofactor, and some other terms that these do not involve X11. And this also doesn't involve X11. So if you look at the derivative of this determinant at this matrix, let's call this matrix A instead of, maybe this is little a. Okay, so determinant with respect to X11 at A right? So sort of you're trying to find the derivative of the determinant at A. So that's just this determinant of this cofactor. Okay, and so if your determinant is 1, then one of these guys, so this is I've just written for x11, but you can change it into xij. So each of these xij's, the derivative of this determinant with respect to partial derivative is going to be some determinant of some cofactor here. So now the point is that all you need for one, so this derivative having determinant, the derivative of the determinant having full rank is that one of these is non-zero. Okay, because you're talking of the determinant map is from something to R. Okay, and so you want the derivative to a full rank. Here it is full rank just means rank 1. All right, so so you want one of these to be non-zero, but that's guaranteed if you know that the determinant is 1. If the determinant is 1, then all of these cofactors can't vanish because then your determinant would be 0. All right, so anyway, so it's easy to check that this full rank condition, this condition of being a submersion, actually holds for the pre-image of this of 1. Okay, and so this is why this map, this is called a special linear group. Okay, so this is G is the general linear group, and this is the this is called the special linear. So this is also an example of a Lie group. Yeah, and I know, of course, here it's also easy to check in all these examples, GLN and SLN, that this multiplication map and inversion map, these are smooth maps. Okay, so they are. So that's something that you already know. Okay, anyway, so we'll see more examples of Lie groups later, but there are some simple examples to start with. So next time we'll talk of tangent spaces and make sense of the notion of derivative of smooth maps between manifolds. And then we'll go on to talk of submersions and immersions and prove the Whitney embedding theorem. So that's the plan. Let me stop here. If there are any questions, feel free to unmute yourself.